Hey everybody, Trey here. Welcome back to another video. As many of you know, the EF5 drought is over. A few days ago, the National Weather Service office in Grand Forks upgraded the tornado that occurred near Enderlin, North Dakota on June 20th, 2025 from an EF3 to an EF5, an upgrade that shocked many around the weather world. Given the historic nature of this event, you know it's time for a meteorological breakdown. In this video, we're going to dive deep into the meteorology behind this setup that spawned the first official EF5 in the US in 12 years. We'll take a look at the factors that set the stage for such an impressive localized outbreak, the threat of which was quite conditional at first, and we'll compare some of the forecasts and model data leading up to the event with what actually happened. We'll also dig into the radar data from this day to analyze the intricate convective evolution of the tornadic supercells. And if you've watched my breakdowns for a while now, you know I really don't touch on damage too much, but we'll talk about what went into the EF5 upgrade, and I'll give you some of my thoughts on it as well. And of course, the tornadoes were only part of the story on June 20th. We'll also discuss the evolution of the high-end Derecho that rolled across North Dakota behind the tornadic supercells, producing widespread damage via straight-line wind gusts in excess of 90, even 100 miles per hour. All in all, an incredibly intricate, complex collection of factors came together to make this event what it was, so this video is going to be a long one. Sit back, relax, and let's learn about what made the June 20th event a historic one. The Storm Prediction Center first outlined a risk area for June 20th in their Day 3 outlook on June 18th. A large level 2 out of 5 slight risk was drawn from North Dakota eastward into the Great Lakes, coincident with a 15% hatched area indicating the potential for significant severe weather. An upgrade to level 3 out of 5 enhanced risk was made from far eastern Montana into Minnesota with the midday Day 2 outlook on June 19th. Tornado probabilities remained somewhat low at 5%, but 30% hatched areas for very large hail and significant damaging winds indicated that a potent event was possible. The enhanced risk remained with the initial Day 1 outlook on June 20th, but tornado probabilities were upgraded to 10% hatched from central North Dakota into Minnesota, suggesting the potential for strong tornadoes. As it became apparent that a damaging derecho was imminent, an upgrade to level 4 out of 5 moderate risk was made with the 1Z Day 1 outlook, driven by an increase in damaging wind probabilities to 45% hatched. All in all, 23 tornadoes occurred across North Dakota on the 20th, most of which occurred from discrete supercells ahead of the impending derecho. 6 of these were strong EF2+. Tornadic activity began just before 2Z, 9 p.m. Central Daylight Time, with a brief, weak tornado near Spiritwood just east of Jamestown. This led to one of the most notable tornadoes of the outbreak, the photogenic EF3 near Spiritwood and Urbana. Subsequent EF2s occurred near Valley City and Fort Ransom before the Enderlin EF5 began around 11 p.m. We'll get into the damage later, but winds were estimated to be above 210 miles per hour. An additional EF2 began near Enderlin as the EF5 was dissipating, after which the derecho overtook the tornadic supercells and damaging straight-line winds became the main hazard. Before we move on, I wanted to remind you about my new site, stormchasercoaching.com. Here you can find the most in-depth educational content specifically tailored to help you improve your storm chasing skills, created by some of the best storm chasers and meteorologists in the world. If you're someone who wants to start your storm chasing journey safely and effectively, or you're a veteran chaser who wants to improve your game, Storm Chaser Coaching is for you. To help you get started, we're giving you our entire Storm Chasing 101 course for free. That's right, that's 2 hours of in-depth content taught by me that lays out all the basic foundations you need to chase safely and successfully, completely for free. Check out the link in the description box below to access our Storm Chasing 101 course. Also, join our free Discord community to connect with our coaches and other like-minded severe weather enthusiasts at the link in the description. For more information on what else we have to offer, visit stormchasercoaching.com. Now, back to the video. Alright, let's dive into the meteorology behind this event. As always, we'll start at 500 millibars at 12Z, 7 a.m. Central Daylight Time on June 20th. As is typically the case as you go farther and farther into late spring and early summer, a large ridge had developed across the southern tier of the U.S. But we still had a fairly active jet stream off to its north, trough here over the northeastern U.S., and a fairly large trough over the western half of the country. Within this trough, several little shortwaves were embedded within the flow. These little kinks in the height contours are little shortwaves within the main larger trough. And the one that was of particular interest to the June 20th event was this one right here out across western Wyoming, just on the northeastern fringe of this little jet streak right here. And as we progressed through the day, the larger trough would move inland a little bit, and the shortwave would move over top of the ridge right into the Dakotas by the afternoon hours. Here we are at 21Z, which is 4 p.m. Central Time, and you see that shortwave right there, pretty well defined from eastern Montana down into western South Dakota. And as we headed into the evening hours, that shortwave would continue to progress across the Dakotas, providing at least some large-scale forcing for ascent to aid in storm initiation in this environment. Now, this was still a pretty subtle shortwave, just a little kink in the height contours there, so synoptic forcing wasn't all that strong, but at least we had some feature synoptically to help us initiate storms in this environment. Up at 300 millibars is where we look for defluence. It's the spreading apart of those wind vectors in the upper levels of the atmosphere which creates a void. And to fill that void, air is brought upward from below, and that's how you get large-scale rising motion that can prime the atmosphere for storm initiation in a given environment. Here is our little jet streak associated with the shortwave of note in the June 20th event. And you'll notice as it rounds the ridge into the northern plains going into the afternoon, we don't see a ton of defluence out ahead of it. Very limited directional change in the wind barbs as that jet streak shifts into the northern plains. Winds across far northern North Dakota out of the west-southwest, same thing as we go to the south across Nebraska and South Dakota. So very limited defluence aloft, and this goes along with the subtlety of the shortwave at 500 millibars. We just didn't have a ton of synoptic or large-scale forcing for ascent, and the question was whether or not this would be enough forcing to help overcome the warm 700 millibar temperatures. This was really the main talking point with this setup, and it's what made the setup so conditional. In the days leading up to the event, it was quite apparent on models that a very volatile environment for tornadic supercells would be in place across the Dakotas on the 20th. But it was very questionable whether or not storms would actually even fire in that environment because of the warm 700 millibar temperatures. 700 millibars is typically where the cap in the atmosphere resides, that layer of warm air aloft that inhibits thunderstorm development. So we can use 700 millibar temperatures as a proxy for the strength of the cap. Just for some context, here are month-by-month thresholds for when 700 millibar temperatures become too warm to support thunderstorm development. This is work done by meteorologist John Davies. I'm sure you've heard his name before if you've watched the channel for some time. He's done a lot of work on cold core tornado setups, but he's also done work on 700 millibar temperatures and their relation to convective initiation. So these values you see below are for each month and what constitutes temperatures that are too warm at 700 millibars to support convective development. Now, these thresholds are not applicable for higher terrain areas, so places like Colorado, Wyoming, etc., where terrain impacts can help overcome warm mid-level temperatures. So for eastern North Dakota, these would be applicable. Davies found that for the month of June, when 700 millibar temperatures are at or above 12 or 13 degrees Celsius, that starts to become too warm for convective development. In the days leading up to the event, models were pretty gung-ho on extremely warm 700 millibar temperatures across southern North Dakota into South Dakota. This is a map of forecast 700 millibar temperatures from the 9Z wrap on June 19th. So basically, this is a map of forecast 700 millibar temperatures valid at 0Z or 7 p.m. on June 20th from the 9Z wrap on June 19th. So an early morning run on June 19th. So about a day and a half to almost 2 days before the main tornadic activity occurred on June 20th. First, here is where the tornadic activity occurred, and we have the color bar at the bottom of the screen here, but I'll go through on the map what each of these contours represents. This yellowish color here, that is the 10 degrees Celsius isotherm. Then we have the 11, 12, 13, 14, and 15 degrees Celsius isotherms there. So our area of interest was characterized by 700 millibar temperatures between about 13 and 15 degrees Celsius, which is well in excess of those Davies thresholds that we talked about a minute ago. And many models were on the same page. So it seemed quite unlikely in the days leading up to June 20th that despite the volatile environment in place, mid-level temperatures would be too warm to support convection that would take advantage of the forecast volatile environment. Even some of the models on the morning of the event were still showing quite warm 700 millibar temperatures. This is the 12Z NAM on June 20th, valid for 7 p.m. that same day. Again, here is the 11, 12, 13, 14, 15, and even 16 degrees Celsius isotherms. So our area of interest on the NAM was still projected to be quite warm, with 700 millibar temperatures of about 14 to 16 degrees Celsius. Same thing on the 12Z GFS from June 20th, with 700 millibar temperatures of about 13 to 14 degrees Celsius in the area of interest. But by the morning of the 20th, some of the models were coming on board with a scenario where mid-level temperatures would not be as warm and prohibitive to convective development. Here are forecast 700 millibar temperatures for 7 p.m. from the 12Z HER on June 20th, and this was a much more favorable look. Temperatures in our area of interest at 700 millibars were about 10 to 13 degrees Celsius, so kind of right on or just below that Davies threshold, which would better favor initiation. Same thing on the 12Z wrap, with temperatures of about 11 to 13 degrees as well. Compare this to the wrap the morning before, and we had seen a much more favorable trend toward cooler 700 millibar temperatures with time, and some of the models were starting to show this scenario, but models were split, which still led to a bit of a lack of confidence in storm initiation across southeast North Dakota. Here we have a series of 700 millibar maps from the SPC Mesoanalysis page, and I want to thank Chris Howell for sending me his personal archive of SPC Mesoanalysis and model data for the June 20th case. Pay close attention to these red dashed lines you see here. These are the 700 millibar isotherms, or lines of equal temperature, and they're labeled for us. This is the 6, 8, 10, 12, 14 degrees Celsius lines, and so on and so forth. Also keep in mind our Davies threshold, 12 to 13 degrees Celsius for 700 millibar temperatures in June. We start off the day with basically 9, 10, 11 degrees Celsius temperatures in that southeast South Dakota corridor. Not a ton of change throughout the day, some slight warming as we headed into the afternoon and evening. But as we go towards 0Z, take a look at where we are. Again, this was right about storm initiation time, and this is the 12 degrees Celsius isotherm in southern and southeast North Dakota. So our area of interest was experiencing 700 millibar temperatures of about 11, 12, 13 degrees Celsius at most. That's kind of right on that threshold, but within that threshold for an atmosphere that's not too capped for convective initiation. So 700 millibar temperatures definitely came in a little bit cooler than expected, siding with some of the models like the HER and the RAP from the morning of the event. Now, after 0Z, mid-level temperatures continued to warm a little bit, but by this time storms were well underway, and they were able to become mature before temperatures became too warm at 700 millibars. And as we've talked about before on the channel, mature supercells can persist longer than you might think into more hostile atmospheric conditions, especially if they became mature before conditions became more hostile. But as storms were initiating, 700 millibar temperatures were within that threshold in southeast North Dakota, leaning toward a more favorable environment for convective initiation. And it just goes to show you how close we might have been to this being a non-event as far as tornadic supercells go. Had 700 millibar temperatures been maybe a degree or two warmer, that's it. The atmosphere may have been too capped and too warm to support the initiation and or maturation of convection. Had 700 millibar temperatures come in at 13 to 14 degrees Celsius, we might not be here talking about the EF5 upgrade or tornadoes in general from this setup. We still would have had the Derecho, storms formed out west on the higher terrain. We're going to talk about that a little bit more in just a bit. So they would have been able to overcome the warmer 700 millibar temperatures fairly efficiently. But out here in the lower terrain of eastern North Dakota, that would not have been the case. So we were literally right on the edge of this being a non-event, at least from a perspective of tornadic supercells in eastern North Dakota. All right, let's head down to the surface. Initially, the pattern was somewhat nebulous, but was expected to become better defined as we headed into the afternoon and evening. Here's how I've analyzed the surface pattern at 12Z. A broad, developing surface low is located across the northern high plains with perhaps a few different low centers within the main surface cyclone. Perhaps the most obvious one was in western South Dakota at 12Z. To the northeast of this surface low center was draped the warm front. Now this warm front was tricky to analyze because there wasn't a well-defined wind shift that usually accompanies a warm front, but there was somewhat of a temperature and moisture gradient across the boundary. Notice to the south of the warm front, temperatures were in the mid to upper 60s and low 70s, whereas to the north, temperatures were in the low to mid 60s. Dew points on the south side of the boundary were also a little bit higher than to the north. Those values were in the low to mid 60s, whereas we had mostly dew points in the 50s to low 60s on the north side of the boundary. Also, if you take a look at the SPC Mesoanalysis archive, you can see a bit of a pressure tongue across this corridor, which is another sign that a frontal zone is occupying that location. The surface low and the warm front were the main features in the June 20th outbreak, so that's what we'll be focusing on with our surface analysis going forward. By 15Z, not much had changed, although we had begun to see a significant decrease in surface pressures, indicating the intensification of the surface low. A secondary surface low center had become a bit more obvious across northern Wyoming, along with our prior center in western South Dakota. The warm front was draped in a similar position to what it was at 12Z, but a separate differential heating boundary had become better defined to the south of the warm front. I've drawn it in as this orange dashed line from southeast North Dakota into Iowa. Notice on the west side of the boundary, temperatures were in the upper 70s to 80s, while on the east side, temperatures were mostly in the low to mid 70s. This was likely due to a rash of overnight convection that had persisted into the morning across Minnesota and Iowa. By 18Z, 1 p.m. Central Daylight Time, the surface low had reorganized as it was deepening, now exhibiting really one main center up there in northeast Wyoming. Pressures had come down even further to about 995 millibars. A dry line was now evident draped to the south and southeast of the surface low, separating much drier air to the west from moist air to the east. And our differential heating boundary had become even more well-defined, with temperatures in the 90s to the west, upper 70s to low 80s to the east. And there was now a little bit of a wind shift associated with it, with a little bit more southeasterly flow on the east side of the boundary. It was almost acting as an effective warm front, which is why I've drawn it in red this time. Now remember, this is subjective analysis. This is how I interpreted the surface pattern. I've seen some folks treat this as just one warm front, but given the fact that SPC Mesoanalysis showed two distinct pressure tongues, leads me to believe that these were two separate boundaries. Easterly winds to the north of the warm front and surface low across eastern Montana and northwest South Dakota provided an upslope regime, leading to higher confidence of storm initiation in this area. As low-level winds interact with higher terrain, they're forced upward, leading to a source of rising motion that can be a very efficient source of storm initiation. This is why warm mid-level temperatures didn't matter so much out this far west, as the higher terrain was able to compensate by forcing air upward within the upslope regime. By 21Z, the surface low had started to move off to the east as it deepened, but our main features of note had not changed position all that much. And by 0Z, 7 p.m., right about storm initiation time, the surface low had moved into northwest South Dakota, with the synoptic warm front draped across southeast North Dakota. And take a look at where that intersection point is between our effective warm front / differential heating zone and the synoptic warm front. Here is Jamestown, North Dakota, and that's right about where our tornadic supercells first initiated. So there may have been a little bit of extra convergence here. Again, this is subjective. This is how I've analyzed the surface pattern. Some folks have considered this to be just one single warm front, but if my analysis is correct, there may have been a little bit of extra convergence right at that intersection point to focus convective initiation in southeast North Dakota. As the low-level cyclone intensified through the day, so did the associated low-level jet. For most of the day, flow across the Dakotas was fairly weak until the late afternoon to early evening hours, when the core of the low-level jet expanded across Nebraska into eastern South Dakota. By early to mid-evening, about 50 to 55 knots of flow was situated across eastern South Dakota into Nebraska, with about 25 to 30 knots of flow across southeast North Dakota. 850 millibar flow would continue to strengthen through the evening during the life cycle of the tornadic supercells, with 50 to 55 knots of flow seeping into southeast North Dakota by 4Z. This set the stage for ample low-level wind shear for storms to work with surface winds out of the east-southeast at 10 to 15, maybe 20 knots, transitioning to 40, 50, 55 knots of flow out of the south-southwest at just a kilometer off the surface. That yields impressive veering and strengthening of the winds with height, favoring significant tornadoes. Alright, let's take a look at some observed soundings from across the region to see how the preconvective environment progressed throughout the day. We're going to take a look at some soundings released from a couple of National Weather Service offices, Aberdeen, South Dakota, and Bismarck, North Dakota, as well as a research sounding from Cooperstown, North Dakota, north of the Spiritwood and Enderlin area. Let's start off with the 12Z sounding at Aberdeen, South Dakota. Aberdeen was a little bit farther south than the outbreak area, but the soundings released there were perhaps most representative of the environment in southeast South Dakota compared to Bismarck. At Aberdeen, we start off the day with a pretty interesting looking sounding. A very stout capping inversion was in place at about 850 millibars. This was at the base of a pretty potent elevated mixed layer, or EML, that layer of very steep lapse rates approaching 9 degrees Celsius per kilometer, between about 800 and 600 millibars. We talk about the elevated mixed layer all the time here on the channel. The elevated mixed layer is that layer of warm, dry, well-mixed air that emanates off the higher terrain out west in places like the desert southwest, the Rockies, etc., and gets transported out east atop the low-level moist layer via the westerly or southwesterly mid-level flow. The EML serves to thwart convective development for much of the day, allowing instability to build and build until the cap erodes fully. Now, this EML was characterized by very dry, very warm air, leading to that stout cap. And this is a cap that might be difficult to erode given the background environment. We certainly might get close with the combination of the forcing from the approaching shortwave, which can help lift and cool the capping inversion, significant warming of the surface temperatures up into the upper 80s to low 90s, and strong moisture advection as those 70s dew points made their way up into the region. But would it be enough to overcome how strong this cap was? If we'd had a very high amplitude, strong trough moving in, I wouldn't be too concerned, but because that shortwave was quite subtle, it was somewhat questionable whether or not it would be enough, along with those other factors, to fully erode the cap. Regardless, we already had quite a bit of instability in the atmosphere, most unstable CAPE of about 1500 joules per kilogram, and assuming strong surface heating and moistening, you'd expect instability to climb pretty high in this environment. Not much to speak of with the wind profile at this point, certainly strong enough deep layer shear to support supercells with a fairly lengthy hodograph, about 50 knots of effective bulk shear, and with somewhat limited low-level curvature of that hodograph, again with the intensification of the low-level cyclone throughout the day and the accompanying low-level jet, you'd expect those hodographs to start enlarging quite a bit by early evening as low-level shear increased. Here now is the 0Z sounding at Aberdeen, so 12 hours later. What had changed? Well, instability, for one, had blossomed. Mixed layer CAPE over 4,300 joules per kilogram, a very, very thick instability profile, one that would certainly support explosive convection should it develop. Lapse rates remained quite steep aloft, 7 to 500 millibar lapse rates at 9 degrees Celsius per kilometer. That is very, very steep, indicative of a robustly unstable air mass. That EML certainly was making its presence felt. Our moist layer had deepened substantially. Now, 93 over 72 at the surface, it was quite well mixed. You see that kind of inverted V profile there. But remember, this is at Aberdeen. It's quite a bit south of our outbreak area. Up in southeast North Dakota at 0Z, temperatures were in the mid-80s or so it would not be this well mixed in the Jamestown vicinity at this time. Certainly well within that 20-degree temperature dew point spread threshold for tornadic activity. But nonetheless, the moist layer had deepened pretty substantially, up to almost 700 millibars, which is quite deep, especially for the northern plains. Now, notice the 700 millibar temperature, still a little bit of a warm nose remaining. If we were to extrapolate our 700 millibar temperature down to the surface, that would give us a reading of about 17 degrees Celsius, which, again, is several degrees higher than what it was in southeast North Dakota, as we discussed earlier. But nonetheless, the cap was fairly negligible, only about minus 25 convective inhibition, which is pretty negligible, especially with 700 millibar temperatures a little bit cooler farther to the north, and our shortwave moving in to provide some forcing to overcome the cap, as well as perhaps that slightly enhanced convergence at that intersection point between our effective warm front and the synoptic warm front as we showed earlier. Taking a look at our hodograph, a very impressive one at that, 50 knots of effective bulk shear, a very lengthy hodograph with an increase in low-level shear. You see that clockwise curvature in the low levels of the hodograph, leading to about 325 meters squared per second squared of effective storm relative helicity, more than adequate to support significant tornadoes, especially coupled with this kind of an instability profile. And those hodographs would continue to enlarge through the evening as that low-level jet continued to ramp up. Let's now take a look at the Bismarck soundings. The 12Z sounding, very similar to what we saw at Aberdeen. Very stout capping inversion, lots of dry air in the low to mid levels of the atmosphere, steep lapse rates aloft. And we actually had a special 21Z sounding at Bismarck, which helps us out a lot here. Interestingly enough, between about 500 and 700 millibars, temperatures actually warmed a little bit between 12 and 21Z. And it almost looks like that it was at the base of some semblance of elevated mixed layer. You see that very uniform layer of very steep lapse rates, kind of straddling the 500 millibar mark. Lapse rates in this layer approaching 9 degrees Celsius per kilometer. The little bit of warming at its base, not really prohibitive to convective development, but it did help destabilize this profile. Mixed layer CAPE above 1200 joules per kilogram, likely locally higher, although we did still have some convective inhibition remaining in this environment. We had seen a bit of a moist layer develop. It was a shallow one, only up to about 850 millibars or so, and overall there was just a lot of dry air in this profile, especially in the low to mid levels. And we'll revisit this later on as we talk about the favorable environmental components for the derecho, but overall a fairly unstable environment with a fairly strong shear profile. About 55 knots of effective bulk shear, a very lengthy hodograph, but much less low-level shear than areas farther east. We were well removed from the low-level jet core in western North Dakota, so low-level shear was very limited, and therefore this profile would much more favor a large hail and damaging wind threat. Moving on to 0Z, and we still had that little bit of warming at the base of the apparent elevated mixed layer near 500 millibars, but it, again, wasn't prohibitive. It's not one of these very well-defined warm noses that we often see, and what we saw somewhat back out to the east. But notice the 700 millibar temperatures here. If we extrapolate that down, it would be about 8 degrees Celsius or so well within that 12 to 13 degree threshold. So if we kind of take a middle ground between the 0Z sounding here at Bismarck, the thermodynamic profile, and the 0Z Aberdeen thermodynamic profile, you get a profile that is pretty much fully uncapped. A little bit of some warmth there at 700 millibars or in the mid levels, but not prohibitive to convective initiation. Again, the Aberdeen sounding 700 millibar temperatures were a bit too warm compared to what they were over the Outbreak area. So if we kind of take a middle ground, you can imagine about a middle ground sounding between Aberdeen at 0Z and Bismarck at 0Z. Extreme instability, 700 millibar temperatures about 11 to 12, and fairly limited remnant capping. That was going to be an environment that would favor storm initiation. Might they struggle to be surface-based initially? Perhaps. We're going to get to that in just a second. But the main key is that mid-level temperatures were not too warm, we had explosive instability, and a forcing mechanism from the approaching shortwave and the warm frontal zones. That was going to be enough to initiate storms in this environment. So the main question we had, would storms even fire? That question had been answered by early evening. And again, kinematically, we were only improving with time with strong low-level and deep layer shear. If supercells could become surface-based, then we were going to be off to the races in an environment that would favor all severe hazards, including significant tornadoes. Here is a sounding taken at 23Z, 6 p.m., about an hour before storm initiation, by a group from the University of North Dakota who were sitting in the town of Cooperstown, which is about 40 to 50 miles north of the Jamestown, Spiritwood, Enderlin areas. A fairly similar look to what we've been seeing so far. Plenty of instability in the environment, mixed layer CAPE approaching 3,000 joules per kilogram. Now again, there was quite a bit of dry air in this environment, so our value of E-CAPE was about 1,600 joules per kilogram. E-CAPE is a measure of instability that takes into account things like dry air entrainment into updrafts. That can actually negatively affect the buoyancy that the actual storm is experiencing. So because we had quite a bit of dry air aloft in this environment, updrafts going up in this environment would entrain quite a bit of dry air. Therefore, E Cape would be quite a bit lower than the actual mixed layer Cape. Again, about 1600 joules per kilogram. But of course, that is more than adequate to support robust updrafts. 84 over 67 at the surface. This was quite a bit north of the actual warm front, so moisture down along the warm frontal zone was probably a bit higher. Also, the moisture depth was probably a little bit higher. You see here the moist layer extends basically up to just above 900 millibars. I suspect it was a little bit deeper farther to the south near the warm frontal zone. Perhaps kind of a middle ground between this and the Aberdeen sounding at 0Z. Aberdeen sounding, of course, very deep moist layer here, extending up almost to 700 millibars. So probably somewhere in the middle between this and the Cooperstown sounding. We did have a little bit of convective inhibition to deal with. A couple of little warm noses there between about 900 and 700 millibars. Mixed layer convective inhibition about minus 70, which is a little bit on the high side. Usually my rule of thumb is anything under negative 50 joules per kilogram is fairly negligible. So a little bit of extra inhibition here to deal with, perhaps not quite as high farther to the south near the warm frontal zone, again where moisture quality was a little bit higher. But overall, a decent looking thermodynamic profile. And our wind profile, again, strong deep layer shear, weak low level shear. In this case, we were north of the actual low level jet core. Low level winds were much stronger to the south. Now, what did our convection allowing models show leading up to the event? Using the Storm Prediction Center's href archive, I've pulled up the convection allowing model output valid at 3Z the evening of the event. So that's going to be 10 p.m. the evening of June 20th. So by this time, the tornadic supercells were well underway in southeast North Dakota, as was the Derecho back to the west. This first batch of output that you'll see is from the 0Z run the evening before the event. So this is going to be the 7 p.m. convection allowing model suite on June 19th. Again, we're looking at images from those runs valid at 10 p.m. the following evening. Starting off with the HER, we see the developing derecho back to the west and some activity here along or just north of the warm frontal zone in Minnesota, but not much in eastern North Dakota at all. Here's the NSSL WRF, again, very intense derecho moving east across North Dakota, but not much at all off to the east as far as supercells go. Here is the WRF ARW, kind of the same thing as what the NSSL WRF was showing. The FE3 being its normal weird self with a bunch of supercells here. Very poor depiction of what was expected to happen. We were expecting a derecho ongoing by this point, and we just don't see that with this model. Same thing with the NAM nest, kind of all over the place with quite a bit of convection in eastern North Dakota, but the NAM nest does tend to be way too aggressive with convective coverage. So overall, the evening before, we had multiple models showing a derecho moving east across North Dakota without much activity as far as supercells go across eastern North Dakota, likely owing to warm mid-level temperatures. Let's now move on to the 12Z convection allowing model suite on June 20th. So this is going to be the 7 a.m. model suite on the day of the event. Again, still valid for 10 p.m. on the evening of June 20th. Here is the HER, and we're starting to see a little bit better signal for convection in eastern North Dakota. Robust convection at that. You see a very robust supercell there in east central North Dakota with a nice updraft helicity streak indicating that it is a supercell. But note its position. For some context, this is where our tornadic supercell activity ended up being in southeast North Dakota, and the HER was depicting storms well north of that. I'll demarcate where those storms were occurring on this particular model run, and then we'll compare it to where our frontal zones were. So there's where the storms were occurring, and you can see where the warm front is, the surface low back here in western South Dakota, with our warm frontal zone draped up into southeast North Dakota. A little bit difficult to pinpoint it, but our pressure tongue's kind of right in there. So these storms were well north of the warm frontal zone, the synoptic warm frontal zone. So it's likely that these storms being depicted by the HRRR were elevated well north of the warm front. This is something you have to take into account every time you look at convection allowing model data. Where are these storms being depicted relative to your important features? We see the same thing with the ARW model. Derecho moving in from the west with supercells north of the warm front in eastern North Dakota. FV3 on board as well, developing derecho west, supercells even farther north on the FV3 model, likely to be elevated. The NSSL WRF not really gung-ho with anything off to the east of the Derecho, maybe some attempts at convection across northeast South Dakota, southeast North Dakota, and the NAM nest being a little bit overly aggressive here as well. So even though we did have multiple models starting to come on board with more convection in eastern North Dakota, it was likely to be elevated well north of the warm front, and the SPC even mentioned this in their 20Z convective outlook. They said that confidence in surface-based storm initiation remains quite low in eastern North Dakota and western Minnesota owing to warm mid-level temperatures, and that perhaps a more plausible scenario was for scattered storms from low-level warm advection during the nighttime hours in eastern and central North Dakota that would likely be elevated. So looking back, it's pretty clear how we were able to get supercell initiation. Capping was manageable, maybe not zero, but negligible enough for storm initiation. We're going to talk in a second about how it impacted storm evolution, but overall, mid-level temperatures came in cooler than expected and ended up not being as much of an issue as initially thought. And because capping was manageable, we had plenty of forcing from the shortwave and the warm front and that potential intersection point between the warm frontal zones. Had the capping been a bit stronger or the temperatures in the mid-levels a bit warmer, we would have needed a more robust, higher amplitude trough or stronger surface convergence to help overcome the capping, but because it was fairly minimal, that subtle shortwave and the convergence along the warm front were just enough to initiate storms. And we knew that the environment was becoming more volatile with time. The environment was characterized by strong to extreme instability and strengthening low-level shear as that low-level cyclone and associated low-level jet ramped up. So the chances for supercell initiation were becoming higher and higher by early evening. The question that remained was, how would storms evolve? Let's take a look at some satellite data to help us answer that question, starting with the period surrounding convective initiation. Just for some context, this loop starts at 23Z or 6 p.m. Central. Initiation occurred just before 7 p.m., and the first tornadic activity from the southeast North Dakota supercells occurred just after 8:30 p.m. At 23Z, supercells were already well underway in eastern Montana. This was not surprising given the higher terrain and the earlier timing of the shortwave out there. Focusing in on the South Dakota-North Dakota border region, notice this band of stratus clouds. This is indicative of large-scale forcing for ascent starting to impinge upon the region. This was noted by the Storm Prediction Center in their mesoscale discussion covering the eastern North Dakota severe threat. These stratus quickly evolved into horizontal convective rolls, these lines or cloud streets that you see here. Horizontal convective rolls indicate lingering stability in the environment, so that convective inhibition and capping we were talking about earlier, while it was manageable, it wasn't zero. So we still had a little bit of stability to deal with in this environment. Still, storms were able to initiate on the northern fringe of the convective rolls. Here's a view from the ground. These photos were taken right at the time of convective initiation in Medina, North Dakota, which is about 25 miles west of Jamestown on Interstate 94. You can clearly see the lines of cumulus indicative of the horizontal convective rolls and the updraft that would eventually become the Spiritwood tornadic supercell going up on the very northern fringe of the cloud streets. By all eyewitness accounts, development was quite explosive, although it did take a few attempts for the initial storm to take hold. As you can see in this time lapse, multiple updraft pushes go up and then kind of fizzle out before we see a couple of really robust pushes toward the end, signifying that the storm is finally maturing. The updraft was quite tilted, indicating strong deep layer shear within the environment, but also that the storm was potentially struggling with some convective inhibition. Oftentimes when this is the case, an updraft will try to go up, but because it lacks robustness due to the lingering convective inhibition, it's essentially blown over or toppled over by the strong mid and upper level winds, leading to that drastic tilt until the inhibition subsides or is overcome. Once the updraft started to mature, it quickly attained supercell characteristics, which was not surprising given the strong instability and deep layer shear. Note the classic bean shape on radar. Also, note how the storm moved off to the north initially. This means it was moving north of the warm front. In many cases, this would be detrimental to storm intensity and longevity because the environment north of a warm front is typically much more stable. However, this was not the case here. We'd seen ample sunshine on both sides of the boundary through the afternoon, and there was ample moisture pooled north of the front as well, meaning that the environment north of the warm front was not prohibitively stable. By this time, a second storm had also developed to the south-southwest of the northern storm. This would become the Enderlin EF5 producer. Given where these storms initiated, within the area of cloud streets and lingering stability, you'd expect these storms to be elevated, and that was clearly the case visually. First, notice all of this gray, flat, stratusy cloud matter feeding into the storm, which itself has a very flat, featureless, ill-defined base. These are classic signs that the storm is elevated, rooted above that lingering low-level stable layer. You can clearly see how smooth and laminar the base, and really the entire structure of the storm is. It lacks that raggedness and any notable features at all, such as lowerings or scud. It's completely smooth, a telltale sign that the storm is elevated. But things would soon change. About 10 minutes or so after the end of the last time lapse, the storm looked like this. It had undergone a complete change of character. Overall, the storm looked much less laminar, and the base had vastly improved. Notice how it looks much more ragged. There's a distinct lowered area, scud rising into the base, and clear low-level rotation. Here's a view underneath the base, and you can see it has that roiling nature to it, and has much more definition versus what it looked like earlier. So the storm had quickly become surface-based. Something had to happen in that short time span to transform the storm from this elevated piece of garbage, frankly, to this beastly surface-based supercell. One hypothesis is that the increasing low-level shear and storm relative helicity with time helped to overcome the convective inhibition. Now, we've talked about this before on the channel, particularly with nighttime events. Usually at night, convective inhibition increases with time as you go past sunset, but if you have strengthening low-level shear and storm relative helicity with time, that can help overcome the negative contributions from convective inhibition and yield surface-based supercells despite that capping. And before, I've explained it as storm relative helicity adding to the buoyancy of the environment beyond what our measures of instability like CAPE can show us. But that's a little bit of an oversimplification, and we've never really gone into why this is the case physically. So let's go ahead and do that. So let's say we have a supercell in the thermodynamic environment you see on the left, which is characterized by very strong instability, but we do have a little bit of convective inhibition in this layer here. You see that little warm nose there. That is convective inhibition or capping. Now let's assume we have an air parcel that's going up in this environment. We can assume the accelerations that the parcel is going to experience based on the thermodynamic profile. In this layer, where we have all of this instability, the parcel is going to be able to accelerate upward. That's what positive buoyancy is. It's the ability of an air parcel to rise on its own. But in this layer, where we have all of that convective inhibition, the parcel is cooler than the environment around it, therefore it's going to have a tendency to accelerate downward or sink, which normally prohibits surface-based convection and can prohibit convection altogether. If you have an air parcel rising from the surface, well, it's not going to be able to really penetrate through that layer in a lot of cases. But air parcels that are rooted above this capping inversion can rise on their own. That leads to elevated storms. Now, a supercell is characterized by a mesocyclone, a rotating updraft. And the mesocyclone extends from the low levels of the storm all the way through the storm's depth. Now, this mesocyclone is an area of low pressure. One of the basic tenets of meteorology is that air flows from high to low pressure. When you have a concentrated area of low pressure within the mesocyclone, the pressure at the ground is going to be much higher. This creates a pressure gradient force from the ground upward into the mesocyclone. Low-level storm relative helicity is a modulating factor of the strength of the low-level mesocyclone. So when you have stronger storm relative helicity, the mesocyclone, and therefore the low pressure that characterizes the mesocyclone, is stronger, and therefore that upward directed pressure gradient force is stronger as well. So therefore, in an environment of strong storm relative helicity, combined with a little bit of capping, that storm relative helicity can help overcome the negative contributions from convective inhibition because of that strong pressure gradient force, meaning that we now have strong upward accelerations through the entire column of the atmosphere, rendering the tendency for sinking motion in that layer of convective inhibition negligible. That's how supercells can overcome convective inhibition and become surface-based in environments of strong low-level storm relative helicity. And once the storms became surface-based, it didn't take long to start producing tornadoes given the extremely favorable background environment. About 10 minutes after the last clip you saw, the northern storm wrapped up significantly, producing a brief, weak tornado near Spirit Wood at 8:34 p.m. At 8:51, the storm would produce the first significant tornado of the event outside of the Derecho, a large, long-lasting, photogenic EF3 between Spirit Wood and Urbana. This was likely induced by the first in a series of storm interactions that would take place throughout the life cycle of the southeastern North Dakota supercells. Based on research by Cameron Nixon, purely isolated supercells rarely produce significant tornadoes. Supercells need a perfect balance of inflow and outflow to become tornadic. To balance out the inflow going into a supercell, you need a source of outflow. Where does this outflow come from? Auxiliary cells in proximity to the main supercell. As the northern supercell was maturing, so was the southern supercell. Nixon et al. 2024 found that in supercell pairs, the lead supercell has a much higher likelihood of undergoing significant tornadogenesis versus the trailing storm because of the trailing storm's outflow contribution. Here, the southern storm was likely able to nudge the northern storm toward tornadogenesis. As the Spirit Wood EF3 was ongoing, the southern storm produced a brief, weak tornado near the town of Adrian. Near the end of the Spirit Wood tornado's life cycle, the northern storm also produced an anticyclonic tornado near Sanborn. It was associated with the new mesocyclone that developed as the Spirit Wood tornado was occluding, and it was coincident with an anticyclonic hook, essentially a backwards hook echo. This gave way to a long-lived EF2 near Valley City as darkness began to fall. At this point, the configuration of the two supercells became less and less favorable for continued tornado production in the northern storm as its inflow became increasingly impeded by rain-cooled, stable air from the southern storm. No longer was the northern storm the lead storm in the pair, leading to its demise and the intensification of the southern supercell. During this time, the southern storm began producing significant tornadoes, the first of which was an EF2 near Fort Ransom. Then, after an approximately 30-minute lull in tornadic activity, the main event happened. The tornado that ended the 12-year EF5 drought, the Enderlin EF5. It was a large tornado, over a mile wide at times, and it remained in progress for nearly 20 minutes. Immediately after the EF5 dissipated, a second significant tornado developed northeast of Enderlin and tracked toward the town of Coburn. After this, the impending derecho would overtake the supercells, signaling an end to significant tornado production. At this point, the Fort Ransom tornado was ongoing, and again, the Enderlin EF5 began at 11:02 p.m. Notice how the southern supercell didn't really have any auxiliary cells around it to help nudge it toward tornadogenesis like the northern storm did. Sometimes when the environment is high-end, like it was on June 20th, it just doesn't matter. Sometimes supercells will produce tornadoes regardless of the amount of auxiliary cells. But there were some interesting things that happened on the storm scale in the lead up to tornadogenesis of the Enderlin EF5. At 10:28 p.m., a small area of precipitation appears in the inflow notch of the southern supercell just off the forward flank. Now, it's difficult to know if this was a completely separate shower that developed, or if it was just a pulse of the main supercell's updraft, but nonetheless, it seems to have had an impact on the southern storm's evolution. Over the next several scans, the convective element kind of blows up and conjoins with the forward flank of the supercell, causing it to go from a storm with a disheveled, dog-leggy type appearance to one that appears much healthier and much more shapely. Also during this time, the derecho was approaching fast from the west. I don't think it's a coincidence that the southern supercell underwent significant tornadogenesis as the derecho got closer and closer. This is a relatively common, more indirect interaction that often induces tornadogenesis. Unsurprisingly, the Enderlin EF5 exhibited an impressively intense tornado vortex signature, or TVS, throughout its life. We can estimate a tornado's intensity using radar velocity data, starting by calculating a variable called delta V, which is essentially the total wind shear across the TVS. In mathematical terms, it's the difference between the maximum outbound and maximum inbound velocity within the vortex signature. However, the relationship between delta V and tornado intensity is an outdated concept, and recent peer-reviewed research suggests that rotational velocity, or VROT, is a much better proxy for tornado intensity from radar data. VROT is simply half of delta V, and when combined with an estimate of tornado potential in a given environment, specifically significant tornado parameter or STP, it can give us an estimate of tornado intensity in real time, as illustrated in Smith et al. 2020. I went through and manually calculated VROT for a few scans during the Enderlin EF5's life, particularly surrounding the time at which the EF5 damage indicators occurred, which was 11:06 p.m. The velocity data was quite noisy at the lowest elevation angle during the 11:08 p.m. scan, so for this scan I used the velocity data at tilt 2, which was about 9,000 feet off the ground compared to about 5,000 feet off the ground at the lowest elevation angle. Technically, only data at the lowest elevation angle should be used for this technique, but for our purposes it should be adequate, keeping in mind that there's typically a slight decrease in winds as you get closer to the surface. During this stretch, VROT values exceeded 80 miles per hour, with the 11:08 p.m. scan registering an extremely impressive 107 miles per hour. The significant tornado parameter was around 11 at this time. The STP bullseye in SPC mesoanalysis data was erroneously displaced from where the Enderlin supercell occurred, so I used STP values from proximity soundings near the time of the tornado. Using Figure 9 from Smith et al. 2020, which shows box and whisker plots for certain combinations of STP and VROT, compared to peak wind speed via damage indicators for tornadoes satisfying each STP-VROT combo, we can see that the Enderlin tornado falls into one of these box and whisker plots here, which represent tornadoes in environments with STP greater than or equal to 6, and VROT values greater than or equal to 70 knots or 80 miles per hour. For these upper echelon STP-VROT combos, population density is factored in, with the leftmost plot of these two representing tornadoes in population density less than 20 people per square kilometer, while the rightmost plot represents those in population density greater than or equal to 20 people per square kilometer. The Enderlin tornado occurred in an area of extremely low population density, thus placing it in the left-hand bin. Most tornadoes satisfying these thresholds tend to produce damage-estimated wind speeds between about 120 and 160 miles per hour, obviously quite a bit lower than the assigned EF5 rating. However, Smith et al. Found that low population density tornadoes that satisfied this STP-VROT combo for more than 15 minutes, as the Enderlin tornado was, were much more likely to produce damage-estimated winds in the upper half of the distribution, inching closer to that EF5 threshold. And also, non-traditional damage indicators were used to make the EF5 determination in the Enderlin case, which we'll discuss further in a bit. Regardless, the radar data confirms the fact that a strong to intense tornado was ongoing. Alright, let's take a look at some RAP model soundings in proximity to the tornadic supercells to see what kind of near-storm environment these storms were experiencing, and to see what kind of an environment can make an EF5. These were made using Kyle Gillette's wonderful SounderPi sounding analysis tool. You can go to the website at the bottom of the sounding here to plot your own soundings. This is a sounding taken from out ahead of the northern supercell at 2Z, so 9 p.m. Central Daylight Time. This would have been as the Spiritwood EF3 was ongoing. And this is truly an upper echelon type of profile. Massive instability, mixed layer CAPE at 4,500 joules per kilogram, and even if you take into account the effects of dry air entrainment via E-CAPE, like we talked about earlier, that number only drops to about 3,800 joules per kilogram. So regardless, very, very strong instability in the environment, coupled with very strong low-level and deep layer wind shear. 0 to 6 kilometer shear at over 60 knots, which is more than adequate for organized convection, including supercells. And low-level shear had strengthened dramatically during the day, as we have discussed in this video. Look at that hodograph, just an absolute meat hook of a hodograph with ample clockwise curvature in the lowest few kilometers, and effective storm relative helicity at 530 meters squared per second squared. So you can see that this is a slam dunk significant tornado environment and a truly, truly rare parameter space. Now, we did have some convective inhibition to deal with, mixed layer convective inhibition at about minus 100 joules per kilogram. You see that little bit of a warm nose there just below 800 millibars. This was likely quite a bit less a couple hours earlier as storms were ongoing, but as is typical, convective inhibition usually increases the farther you go into the evening, thanks to the loss of daytime heating and the cooling of the surface. But by this time, the supercells were mature, again, likely drilling through that stable layer because of such strong low-level storm relative helicity. And as we've talked about on the channel before, Mature supercells can last quite a bit longer than you might expect into a more hostile environment, and this was certainly no exception. Moving on to 4Z in the inflow of the Enderlin supercell. This was basically right at the time that the Enderlin EF5 began, and we had maintained that upper echelon profile. Interestingly enough, if this is accurate, we'd actually even destabilized further, with mixed layer CAPE now approaching 5,200 joules per kilogram, ECAPE at 4,200. Again, these are just model initializations, so it could be a little bit off, but it is very interesting to note that we may have even destabilized further the later we went into the evening, which is quite unusual after losing your main source of heating for so long. But nonetheless, gigantic instability with gigantic low-level shear, 0 to 1 kilometer storm relative helicity approaching 500 meters squared per second squared. Large looping hodographs had persisted with strong deep layer shear. Again, just a slam dunk significant tornado environment. We did have increasing convective inhibition with time. That warm nose now much more pronounced. Mixed layer convective inhibition at minus 250 joules per kilogram, which is a lot. But again, the storms were already mature, and the dynamics associated with such strong low-level storm relative helicity allowed for those storms to remain surface-based and continue to produce significant tornadoes. So aside from the convective inhibition, this is a pretty textbook significant to violent tornado sounding with such strong instability and such strong low-level shear. Now, you may have noticed in a lot of photos and videos of the supercells on June 20th, particularly the Enderlin supercell, that they had quite impressive structure. The updrafts were quite sculpted, had striations, etc. This was the result of the combination of lingering convective inhibition with ample streamwise vorticity in the environment. Purely streamwise vorticity exists when your storm relative wind vector, drawn from the storm motion to the level of interest on the hodograph, is parallel to the horizontal vorticity vector at that level, which is perpendicular and to the left of the hodograph. The more that these two vectors are parallel, the higher the streamwise vorticity at that level. The SounderPy program actually plots the percentage of streamwise vorticity in specific layers of the atmosphere, and as you can see here, we had quite a high percentage of streamwise vorticity, generally above 70%, in those lowest few kilometers of the atmosphere. Not only does streamwise vorticity aid in tornadogenesis in supercells, but it also sculpts and striates an updraft when coupled with convective inhibition. This is the classic combination for epic storm structure days. The lingering convective inhibition helps to, number one, clear out all of the junky clouds and convection around the supercell, and number two, it helps to really carve out those layers and striations within the updraft. So while the impacts of convective inhibition were negligible for tornado production in this setup, it did lend the storms their impressive structure. You may have also noticed that several of the tornadoes exhibited extremely deviant motion, moving well to the north or left of their parent supercell's track. This can be attributed to the wind profile. Nixon and Allen 2021 came up with a method to determine the deviant tornado motion vector, which essentially measures how much a tornado is likely to deviate from the general storm motion in a given environment. Now, SounderPy actually plots the deviant tornado motion vector for us, but where does it come from? Using the technique discussed in Nixon and Allen 2021, we first start by finding the mean wind in the lowest 500 meters of the atmosphere. So here is our 500 meter point or half kilometer point, and we're essentially finding the average wind in that layer. Just eyeballing it, it looks to be somewhere in here. We then find our storm motion, and most of the time we can use the bunker's right mover storm motion. If you have an observed storm motion, it is a little bit more accurate, but for our purposes here, the right mover storm motion is adequate. So that would be right in there. And then we simply find the midpoint of those 2 points, which would be right in here. We then draw a vector from the origin toward that point, and that would be our deviant tornado motion vector. And we can compare it to our storm motion vector to see how much tornadoes are likely to deviate in a given environment. And as you can see here, this is using the 2Z wrap proximity sounding ahead of the Spiritwood EF3, which deviated significantly to the north, and we can see why from our analysis. The deviant tornado motion vector is pointed toward the north-northwest, well to the left of the storm motion vector. Here is the 4Z wrap proximity sounding near the Enderlin EF5, which also deviated significantly to the north. Let's first find our 500 meter average wind, which is about right in here. Here is our storm motion, and the midpoint of those 2 points would be about right in there. So our deviant tornado motion vector would once again be well to the left of our storm motion vector, showing us why the Enderlin tornado and many others in this event deviated well to the left of the storm motion. Many of you have astutely pointed out that the Enderlin EF5's path was almost identical to that of another infamous EF5, the Greensburg, Kansas EF5 from May 4th, 2007. Both tornadoes initially followed storm motion closely before turning sharply to the north and almost looping back on themselves toward the end of their life cycles. Let's compare the near-storm environments with these two tornadoes to see if there are any similarities, focusing mostly on the wind profile. Here is the Enderlin proximity sounding, as we've seen so far already in this video. Large looping hodograph thanks to that strengthening low-level flow with time. Our near-surface winds were very nicely backed out of the southeast, veering to south-southwesterly at 1 kilometer, and that low-level flow was quite strong, 35 to 45 knots, about a kilometer or so off the surface, evidence of that strengthening low-level jet with time. Storm motion was about 27 knots toward the east-northeast, which is about 31 miles per hour, so not super slow but not fast by any means either. All of this led to a deviant tornado motion vector well to the left of the storm motion. Let's compare this to the environment near the Greensburg EF5 in 2007, and we have a very similar looking hodograph. Again, a very large looping hodograph, nicely backed low-level flow veering and strengthening with height, and a very strong low-level jet. About 35 to 40 knots or so of low-level flow, and in this case the low-level jet was rapidly strengthening with time as well. And look at that, our bunker's right storm motion at 27 knots, again about 31 miles per hour, so not super slow but not fast either. As a result, the deviant tornado motion vector in this case had a strong northward component well to the left of the storm motion once again. So overall, the wind profiles in these two cases were quite similar. Large looping hodographs expanding in size with time thanks to the increasing low-level jet with time, and a relatively slow storm motion. This seems to be the optimal combination for deviant tornadoes. Now, the low-level jet tends to increase most notably in the central and southern plains, which is where deviant tornadoes tend to occur most often, but the June 20th setup was able to replicate this kind of a profile with that strengthening low-level jet with time, leading to a wind profile with a very deviant tornado motion. Now, what causes this drastic loop toward the end of the life cycle? Well, let's go through the entire path of these tornadoes to see what forces are acting upon the vortex. At first, the tornado follows the storm motion fairly closely, which is expected. But then the occlusion process starts. You can see the kink in the paths of both the Greensburg and the Enderlin tornadoes fairly early on in their life cycles. The occlusion process is when the rear flank downdraft wraps completely around the tornadic vortex, cutting it off from the warm moist inflow it needs to survive. When this happens, it effectively detaches from the parent mesocyclone. So the parent mesocyclone continues to move off to the northeast in this case, but the tornado itself starts to move off to the left or north of that vector. Once the occlusion process begins, the tornado is advected or pushed by the low-level flow off to the north. That is the main force that's acting on the vortex as the occlusion process occurs. The low-level south-southwesterly or southerly winds push the tornado in that direction. Then, toward the end, the tornado starts orbiting around the mesocyclone. That's what creates such a drastic loop toward the end of the path. The vortex orbits around the low-level mesocyclone like a carousel or merry-go-round, and that's how the loop occurs. Alright, let's now talk about the EF5 upgrade, what went into it, and some of my thoughts on it overall. Now, as you know, I'm definitely not an engineer, so this is not going to be a detailed mathematical or physical breakdown of what happened. More so just giving you the details of what went into the upgrade based on the damage surveys that have recently come out. If you're looking for more in-depth physical analysis, there are many better sources for that on the web, including Ethan over at June 1st. I know he's done a video or two on this upgrade, but I at least wanted to mention what went into the EF5 determination with this case. So here's what we know. The Enderlin tornado derailed 33 train cars just southeast of town, 19 grain hopper cars that were fully loaded, and 14 tanker cars that were empty. 5 of these cars were actually pulled into a field away from the track. One of the fully loaded grain hopper cars, which weighs about 286,000 pounds, and 4 of the empty tanker cars, which weigh about 72,000 pounds each. One of the empty tanker cars was tossed 600 to 1,000 feet from the track and approximately 476 feet from the end of the previous tanker car it was attached to. And you can see by all the sets of wheels on the ground that it detached pretty early on in the derailment process. Using similar calculations to those performed in Miller et al. 2024, which discusses how to estimate tornadic wind speeds using the trajectories of large compact objects, surveyors found that winds potentially in excess of 266 miles per hour would be needed to loft the empty tanker car that great of a distance. Surveyors also found that winds of about 230 miles per hour are needed to completely overturn the fully loaded grain car. Both of these are, of course, well past the EF5 threshold. Now, some physical assumptions were made when making these calculations, and it's unlikely that the empty tanker car was lofted the full 476 feet. In fact, it may have even rolled most of that distance based on some of the divot patterns in the field. But just the overturning of the 286,000-pound fully loaded grain car is more than enough to satisfy EF5 criteria alone. And this upgrade was made after months of analysis from some of the field's top meteorologists and engineers, so I trust that this was the right conclusion. In any case, it's nice to see these non-traditional damage indicators added into the fold in post-event damage surveys, and hopefully this trend continues into the future. Alright, now that we've discussed the tornadic activity in detail, I wanted to briefly touch on the meteorology behind the derecho. The tornadic supercells were impactful in their own right, but the derecho was much more impactful on a much broader scale, packing 90 to 100 plus mile an hour wind gusts over a broad swath of central and southern North Dakota into Minnesota. Now this video has been a long one, so I don't want to spend too much time on the derecho, but I did want to give some insight into what caused the derecho to occur and why it was so intense. We're not going to go too much into the science behind derechos. If you're looking for a crash course, check out my breakdown of the 2020 Iowa derecho, link in the description box below. As we discussed earlier, the subtle shortwave embedded within the main trough provided plenty of forcing for this event, including the storms that would fire across the higher terrain of eastern Montana. You can see that by 19Z, that shortwave was nicely ejecting right into our area of interest in eastern Montana and northeast Wyoming, ahead of storm initiation out there. The area out west was entrenched in an upslope regime through the entire day. The winds across western North Dakota and eastern Montana, where the terrain is higher, maintained a significant easterly component throughout the day, which essentially forced that air to rise up the higher terrain of eastern Montana. And when you couple that with the synoptic scale forcing for ascent from the approaching shortwave, it was going to be very easy to get storm initiation in this regime. Convective initiation occurred about 4 p.m. Central Time, and storms quickly became supercellular given strong deep layer shear. Storm coverage and intensity would increase over the next couple of hours as the storms moved into North Dakota. But what kind of environment were they moving into? The first clue that a linear convective complex would develop and therefore favor damaging winds was high temperature dew point spreads. Moisture out west was much more meager than areas east, with dew points only reaching the mid to upper 50s and low 60s, despite strong warm advection. High temperature dew point spreads lead to higher cloud bases, which leads to a better potential for evaporative cooling within downdrafts. The drier low-level air mass indicated by the higher temperature dew point spreads helps to evaporate precipitation as it falls out of a storm. This allows air within the downdraft to accelerate downward, meaning stronger outflow winds that reach the surface. When all of your storms are producing strong outflow in a given regime, those outflows may coalesce, forming one large complex. Now again, much better moisture was situated out to the east, so any complex that did develop would move into that better moisture, which would promote its maintenance. Another clue was dry air aloft. Here is the 21Z observed sounding at Bismarck, North Dakota, and notice how dry this profile is. Again, 88/63 at the surface, very high temperature dew point spreads, but notice how much the temperature profile is separated from the dew point profile pretty much all the way through the atmosphere, with the exception of this little point below about 400 millibars. Really a ton of dry air in this environment, which again favors a lot of evaporative cooling within downdrafts and stronger outflow winds. Much of the same at 0Z at Bismarck, although we had seen a little bit of moistening, Still, the classic inverted V profile indicative of a fairly dry, low-level air mass, 89/64 at the surface. We had maintained those high temperature dew point spreads, and quite a bit of dry air above 700 millibars. Note that we did have strong deep layer shear as well. Photographs were quite lengthy, with effective bulk shear over 50 knots, more than adequate for organized convection, including linear convective systems. Given all the dry air aloft as well as steep low-level lapse rates, which are favorable for more efficient downward transport of strong winds to the surface, downdraft CAPE, or D-CAPE for short, was quite high on June 20th. D-CAPE is similar to CAPE but for downdrafts. It's the maximum energy available to a descending air parcel. Just for some context, D-CAPE values above about 800 joules per kilogram are considered adequate for strong downdrafts, and anything above 1200 joules per kilogram is considered very high and extremely favorable for strong downdrafts. And as you can see, D-CAPE only increased throughout the day across North Dakota. By 21Z, values above 1000 joules per kilogram were common across southern North Dakota, and that would increase towards 0Z with some spots of 17 to 1800 joules per kilogram ahead of the impending derecho. This is extremely impressive and favored intense outflow production with the eastward moving complex. Another potential factor was a differential heating zone or baroclinic zone draped across southwest North Dakota. Of course, we had our synoptic warm front draped from the surface low in northwest South Dakota up into southern portions of North Dakota, but there also seemed to be a secondary differential heating boundary or baroclinic zone draped from southeast Montana into southwest North Dakota. Notice on the north side of the boundary, temperatures in the low to mid 70s, compared to mid to upper 80s on the south side. The farther east you go, 80s on the north side, 90s on the south side. And these baroclinic zones are common features of derecho setups, especially when they're parallel to the mid and upper level flow. The baroclinic zone allows convection to focus along it, and when it's oriented more parallel to the mid and upper level flow, the convection is steered along it for a longer duration, leading to the maintenance of the convective system. So we had many of the basic ingredients needed for a strong convective complex. We just needed the storms to congeal into one. Well, that happened pretty quickly after the storms crossed into North Dakota. The complex rapidly became much more continuous in nature, and after 8 p.m. it began to show signs of a rear inflow jet on radar. A rear inflow jet is a belt of enhanced flow that develops aloft on the back side of the complex and descends to the surface, causing the complex to bow outward and become a bow echo. Again, if you want to know the science behind rear inflow jet formation, check out my 2020 Iowa derecho breakdown. As the rear inflow jet descended to the surface, wind gusts increased dramatically with widespread gusts in excess of 75 miles per hour and several pockets of 90+ mile per hour gusts. There were even some 100+ mile per hour gusts sprinkled in there. Subsequently, the complex evolved into a significant bow echo with an incredibly well-defined bookend vortex on its northern end, giving the system the classic comma shape. Bookend vortices are believed to form via the tilting into the vertical of horizontal vorticity, or spin, by the system scale updraft, after which the Coriolis force, the force imparted by Earth's rotation, tends to intensify the cyclonic vortex on the northern end of the line. Significant damaging winds continued, and eventually the bow echo merged with the tornadic supercells in southeast North Dakota. Interestingly, note how far back the intense winds, denoted by the tan and brown colors, stretch from the apex of the bow. This is somewhat unusual and appears to have been caused by the development of the bookend vortex into a mesoscale convective vortex, or MCV. MCVs are circulations that can develop in the immediate wake of an intense squall line or bow echo. Often they develop on their own, but on occasion, a bookend vortex can morph into an MCV via the aforementioned impacts of the Coriolis force. This was an unusually strong MCV. While they can produce strong winds at their leading edge, rarely do they produce surface winds this intense. After the merger with the supercells, the northern end of the line weakened while the southern end where the merger occurred remained intense. A second bow echo developed from convection ahead of the main derecho, leading to a corridor of intense damaging winds that impacted the Bemidji, Minnesota area. So that's going to wrap things up for this video. Hopefully this gave you a comprehensive look at just how the events of June 20th, 2025 transpired. This was an event where multiple puzzle pieces had to come together just right to give us the outcome that we got, and it was a textbook example of how just a degree or two here or there can make the difference between a blue sky bust and an upper echelon tornado outbreak. The EF5 drought is over, and hopefully we can take the lessons learned from the June 20th event from both a meteorological and damage survey perspective into significant tornado events in the future. Thanks for watching, and we'll see you in the next video.